Okay, so same thing. So what are we going to do with these semiconductors, right? So let's check. Okay, let it be conductors or semiconductors. Okay, you have to apply potential difference. Okay, let's do that. Okay, let's apply potential difference. Let's make this side positive. Let me do that. Let me make it positive, and let's me make this side negative. Okay, so yeah, now think. Okay, properly think and tell me. Okay, what will happen because of the potential difference? The free electrons, let me show you again. Where are the free electrons? This is the free electron, this is the free electron, this is the free electron. What do you think, guys? They'll move to the right or the left?
Left.
Okay, because of this potential difference that we applied, the free electrons obviously are going to move to the left. So free electrons are moving to the left. So tell me the current, right? The current due to the free electrons will be to the left or the right?
Right.
To the right.
To the right.
To the right. Is it okay, this one, guys?
Yes.
Okay. Now, okay. Also think and tell me, huh? Do you agree that there is maybe a germanium here? Yes, there is a germanium here. These 4 electrons it has. Yes, all of them are in the bond. That is also correct. Okay. Do you agree that the negative terminal, right, can push this electron and make it free or not?
Yes, sir.
Okay, the negative is going to
Yes,
push
sir.
the electron. Some of them, not all of them, can push this electron, and this electron can become what, guys? Free. So what do I get, guys, here? A hole. We get a hole here because the electron has left here from here, and that electron, right? Okay, check this. Okay, this electron has already gone to the left, this electron has already gone to the left, this electron has already gone to the left, but this electron, right, while going to the left, right, it can also go back to the what? One of the
Holes.
holes.
Mm.
Okay, and these holes, you know what, they are very good in attracting electrons because they are in covalent bond. Covalent bond is very much ready to pick up electrons. Okay, so it is very easy for this electron to leave from here and go there. Do you agree that the electrons are moving to the left? Yes, free electrons are moving to the left. But do you also agree that I can imagine the hole has gone to the right or not? Check, guys.
Yes, sir.
Where has the hole gone?
Yes. To the right.
To the right. And it is not
To the
true
right.
only for this germanium, it can happen with any of the germanium in this crystal. Okay, so the holes that we are talking about, okay, tell me, where are they moving, to the left or right? To the
To the
right.
right.
Okay, and do you agree with me that they are helping the charges to move or not? Yes, and holes themselves, they can be considered as what charge? Positive charge. So yeah, so that's why we get a current due to holes as well, and that current is called what current? Hole current. And the current is called what, guys? IH. Okay, I think you will agree with me the direction of hole current is again to the right, because holes are positive. When they go to the right, even the current due to holes is to the right. Okay, now look at the electron current and the hole currents. Okay, guys, their motion is opposite, electrons moving to the left, holes moving to the right, but the current that we get because of both of them, right, are in opposite or same direction.
Same direction.
So total current, the total current in a semiconductor will be equal to what? Equals to the whole current plus what current, guys?
Electron
current. Can you understand this? Please don't forget this. Very important for what? For semiconductors. The holes also, they help us in conducting currents. Okay, so this is very, very important. I think you understood till here. Is it clear, guys, all of you, what we have done last class until now?
Yes, sir.
Okay, so yes, any doubts? Anybody wants to ask anything can talk to me. Yes, many of them, they have
No,
not
sir.
attended today. Yes, Rohan, tell me.
No, sir, nothing.
Okay, fine. No, okay, now what is the point of all these things, what we are doing and where we are heading to? Let me just tell you that. Okay, see, okay, I'm going to ask you a question right now. Okay, see, tell me, in this picture, if we get 4 free holes, okay, how many free electrons we are going to get?
4.
4 free electrons. Okay, let me use a notation for that. Okay, let me use NH and NE. Okay, NH represents number density of holes, and NE represents what, guys? Number density of electrons. They have to do with the numbers. Okay, do you agree with me that the NH will be equal to NE or not?
Yes, sir.
Yes,
Okay,
sir.
the number of holes or density of holes will be equal to what, guys? Number density of free electrons. Free electrons. Okay, not electrons, but we have to call it free electrons. Okay, in any semiconductor, when this happens, okay, we call it intrinsic semiconductor. So I'm talking about a type of semiconductor. Okay, don't worry, you will get me. Intrinsic semiconductor, I have another name for it. We can call it pure semiconductor. Pure semiconductor, no impurities. No impurities. Don't worry, you're fine. Okay, check. Look at this diagram that I've drawn, right? Do you notice any other atom, or all of them are germanium atom, guys, here?
All German.
All are germanium. This is germanium, 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 right? So will I call it germanium, or I can call it pure germanium semiconductor?
Pure Germanium.
Pure germanium semiconductor, okay? And this pure germanium semiconductor, okay, has impurities or no impurities? No impurities, no other atoms, okay? And that's why, okay, you can be sure with what, guys? The number density of what? Holes will be equal to what, guys?
Number density of
A
electron.
number density of electrons, and we have a name for them. We call it what, guys? Intrinsic semiconductors. I think till now you are clear with this one. Is it okay, guys, all of you?
Yes, sir.
Okay. Is it okay, guys, all of you? Just check. Intrinsic is clear?
Yes, sir.
Okay.
Yes, sir.
Now this intrinsic semiconductors, they have a problem. I'll tell you what is the problem. The problem is this. Look at this, okay? The moment I draw this band diagram, you should be able to tell me whether it's intrinsic or not. Okay, check. I'm drawing the valence band, I'm drawing the conduction band, and the diagram is 0 or above 0, guys. What do you think? We are never going to talk about 0 anymore. Okay, it is always going to be above 0. That means temperature is greater than 0 Kelvin. This is the conduction band, and this is the valence band. And we know something, right? If I have 4 free electrons, then I'm going to get 4 free holes in the valence band, right? This is the picture, okay? In germanium, we know this energy gap is 0.7 electron volt. I think you agree with the picture, right? This is the picture, right?
Yes, sir.
Okay. This one is clear. Everybody is clear with this, okay? At above 0, you know, at 0 what happens? There's no free electron. So 0 electrons in the conduction band, okay? Now look at the problem. The problem is this. Listen to me carefully, okay? The problem is, yeah, it is a conductor, okay? Yeah, the germanium is a conductor. Silicon is a conductor at this temperature, but the problem is the number of these charges, the holes and the electrons. Do you think is very, very large or very, very small? Is very, very small. You are not going to get so many free charges like metals. Metals, they really have very large number of free electrons, okay? I'm repeating again. Metals, they have very large number of free electrons, okay? And your semiconductor, which I showed you just now, germanium or silicon, they have free electrons, yes. They also have holes which give electricity or current, okay? But the number is what? Number of what, guys? Number of free electron density and the hole density in semiconductor is found to be very, very what? Small. Now you think, will they be good conductors or still they will be poor conductors, guys? What do you think? If the number of free electrons and the number of free electrons and the number of what? Holes is very, very small. So you tell me right now, intrinsic, right? Intrinsic semiconductor, like your pure semiconductor, okay? Pure semiconductor like germanium and silicon. This is the picture for both of them, okay? The number of electrons and the hole is very, very what, guys? Small. So both of them, okay? Tell me, intrinsic, okay? Pure ones. Are they good conductors or poor conductors?
Poor conductors.
They're poor conductors. They are not so good conductors because they don't have very large number of charge carriers, okay? Are you clear with this, guys, all of you?
Yes, sir.
Okay. Naveen has said yes. What about others? Jonavan, Iba?
Yes, sir. Clear, sir.
Yeah, Shelby? Listening? Sonia?
Yes, sir.
Sonia? Sonia is not
Yes,
listening?
sir.
Oh, Sonia is listening. Then 6 is there, 6?
Yes, sir.
Good, you are listening. Very nice, okay. Okay, now say. So, what to do? This is a problem with semiconductors, okay. They are poor conductors, okay, provided they are what? Intrinsic, they are pure, they are poor, okay. Poor conductors, they are pure also, they are poor also, okay, conductors, no. So look at this now, okay. We will do something, okay. We have a method of increasing, look at this, increasing conductivity. We can do this, right? We can achieve this, okay. We can increase the conductivity. We can make a semiconductor which is a pure semiconductor. a better conductor, okay, a better conductor. We can do that by a process which we call it as doping. I'll tell you what is that, okay, doping. And this basically means, okay, see, we can do this, okay, we can achieve this here. See, we can have, I'll just show you very quickly, we can have a large number of free electrons. Look at this. Where are these large number of free electrons, guys? Valence band or conduction band? Can you see?
Conduction band.
Yeah, if I can achieve this, right, you tell me. Now the semiconductor is still poor conductor, or is a better conductor now?
Better conductor.
Better conductor. Or okay, or if I have lots of holes also, what will happen, guys? Tell me. If I have lot of holes also, right, the electrons will be easily moving or not?
Yes.
Yes.
Okay, so there are two ways to increase the conductivity. Okay, either you do what? You increase the number of
Electron.
Free electrons.
free electrons, or you increase the number of what?
Holes.
Holes in the valence band. Okay, if you can achieve this, okay, if you can have a lot of holes, or if you can have a lot of numbers of electrons in the conduction band, the free electrons, then you have made, okay, you have made the semiconductor, what, guys, a better conductor. So how to do it? By a process called what, guys? I told you,
Doping.
Okay, so I will show you now what is doping and how does it increases the conductivity. Okay, how can we achieve this? How can we have a lot of electrons in the conduction band? How can we have a lot of holes in the valence band? That is what I'm going to show you. Okay, for that I need to redraw this diagram very quickly. Just check. So I'm basically talking about doping. Okay, so what is doping? Very simple, I'll just tell you. Doping is a process whereby you add okay, impurity atoms which may be from group 13 or 15, because semiconductors are group 14. Okay, so you are going to add atoms from which group, guys? You'll add group 13 atoms or group 15 atoms. Example I'll give you. Group 13 is gallium. Okay, group 15 atom is what? Potassium. Right, potassium, right? 15, no, potassium, yes. Okay, aluminum is also there. Okay, then group 15, anybody who can tell me? I have only potassium right now.
Nitrogen.
Arsenic.
Arsenic. Cesium.
Who?
Oh no.
Tell me. Arsenic is, I know, is there.
Antimony.
Who? Sorry, I didn't hear you. अरे आवाज क्लियर नहीं है भाई.
SB sir.
SB क्या है? Group 15. Huh? What is SB, by the way?
Sir, antimony.
Antimony is 15. I don't know, huh? But he says so. So let's just take it right now. Okay. so you must be thinking what is going on. Okay, let me tell you. See. Okay. Let me go and draw your germanium properly. Okay, see, let's take up time. Okay, today we'll only do this, so let's not be in a hurry, and we can nicely finish your semiconductors. Okay, check. Your job is just to understand these concepts only. Okay, see. Okay, I'm again drawing the same pure semiconductor, not semiconductors, what I'm saying. Okay, so we have this, we have 4 electrons. Please bear with me so that I draw nicely and talk properly. Okay, see. Same picture, no change. Okay, let's be clear. This is right now. What is this, guys? Intrinsic or extrinsic, guys? Pure or impure? Intrinsic. Okay, and we know, right, when the semiconductor is intrinsic, pure, right, and above absolute zero, some of them will be out, right? The electrons will not be here. Maybe this electron will not be here. Maybe this electron will not be here. So we get holes, right? We know this. We get holes here, and holes here. Okay. So how do we draw energy band diagram? Let me show you back again. See, I know I'm doing the same thing. Okay, you must be thinking, why am I drawing again and again? But this is most important part right now. Please do not lose focus on this. Okay, though it may take some time, but really important. Okay. Okay, so I'm again drawing the valence band and conduction band. We know, right, we already have population of what, guys? Both holes and electrons. If I draw 4 holes here, right, how many electrons should I draw, guys, here?
4.
4. Okay, and this is your valence band, sorry, conduction band, and this is your valence band. What is the energy gap, guys? Let's be clear with that also. For germanium, 0.7
0.7.
electron volts. And what does it mean, 0.7? Let me just quickly tell you. See, can I shift an electron from valence band to conduction band or not?
Yes,
Yes,
sir.
sir.
Okay, what does that mean? That means I have to make who free? I have to make the electron
Free.
free. Going from valence band to conduction band means make the electron free. And for that, energy is required. That means to break the bond, energy is required. How much minimum energy is required?
0.7.
0.7 or more than that. Okay, but minimum is 0.7, right? Okay, so please keep this concept in mind. No, now let me tell you what is doping. Look at this. Now I'm really talking about doping. Okay, so this is the picture of pure germanium. Now I'll do something. See, we have two options. I will come and add a pentavalent. Okay, this group 15 elements are also called what, guys? Pentavalent atoms, and this group 13 atoms are called what, guys? Trivalent. Trivalency and pentavalency. 5 valency, no? 5. And this is what valency? 3.
3.
5 valency means how many outermost electrons, guys? 5, no? And trivalent means how many outermost electrons? 3. Okay, let me show you now what am I going to do. Look at this. Okay, let me remove this germanium from here. Don't forget, I'm adding something here. Okay, I'm adding what now, guys? Look at this. I'm adding pentavalent. Let me do that first. Pentavalent, that means I'm adding phosphorus right now. You guys think and tell me. Okay, phosphorus will come. Okay, this is a free electron. I'm not talking about this. Okay, so this phosphorus will come and bring how many electrons with it, guys? Outermost electrons?
5.
5.
5. Very good. 5. Agreed, right, all of you? Yes or no? All of you agreed?
Yes, sir.
Yes. 1, 2, 3, 4 and 5. Now you tell me. Okay, did I replace some of the germanium atoms? Yes. Is it intrinsic or extrinsic now? I will call it, guys.
Extrinsic.
Extrinsic. Okay, why? Because it is not pure anymore. Okay, now you think and tell me, this phosphorus will go and sit in one of the germanium's place. Okay, and now it will form bond with what? Germanium. So this is the one, right? It's going to form bond here, it's going to form bond here, it's going to form bond here. Okay, do you agree this phosphorus at the most can form how many bonds?
4.
4, because earlier germanium here was forming how many bonds, guys? Averagely 4 bonds. Okay, phosphorus cannot form 5 bonds, no chance at all. If it makes more than 5 bonds, it will rule out the octet rule, no, to become stable. Okay, so it cannot form 5 bonds. Okay, now look at this electron. Please be careful with this electron. You tell me, what is this electron? Tell me first of all, do you agree with me that this electron belongs to phosphorus or germanium?
Phosphorus.
Belongs to phosphorus. But is it forming bond with germanium or not forming any bond with germanium right now?
Not forming bond.
Not forming bond. Can I call it a free electron or not?
Yes, sir.
Okay, all of you agree with this? Just check. All of
Yes,
you
sir.
agree? Okay, this is a free electron and it did not appear because we have broken some bonds. Okay, by breaking some bonds we have not got this free electron. This free electron we just got it because we brought what? Phosphorus, which had so many outermost electrons. Okay, now you have to tell me properly also one more thing. Okay, what about this free electron, guys? Is it same like this free electron or not? Don't forget about this free electron. Okay, this free electron came from what, guys?
Germanium.
From germanium, yes. And this free electron came from phosphorus. Okay, now think and tell me. Okay, do you think these two electrons will have same energy level or same energy values or different energy values?
Different energy values.
Different energy values, because they belong to a different atom. They don't belong to same atom. Okay, so they will have different energy values. Okay, let's be clear with that. This is also free electron, this is also free electron, but this has different energy value, and this electron, free electron coming from phosphorus, okay, this also has different energy value. So I will have to show you how much or where does it have energy value. So I'll go back to this diagram. Let's be clear with this now. Okay, check. Notice I am drawing a red line here. Okay, check. Can you tell me where am I drawing this red line? Red marker. Where am I drawing, guys? Is it on the conduction band of germanium or below the conduction band of germanium?
Below the
Below
conduction
conduction
band.
band.
This is an energy level. Let's be clear. Okay, what is this, guys?
Energy level.
Energy level. Okay, this energy level belongs to whom? Belongs to
Conduction.
not conduction band, not conduction band of germanium. This is conduction band of what? Germanium. This is valence band of what? Germanium. But this electron coming from phosphorus, right, belongs to what? This energy belongs to the fifth electron from where? From phosphorus. Are you clear about this one? It has there, okay. You should not ask me why it has there, but its energy level is found to be lower than conduction band of germanium. It is this much energy this electron has, okay. So look at this. How many phosphorus did I add, guys? Look at this and tell me how many.
1.
So I will get 1 electron from phosphorus here in this level. Can you understand my idea here, or what I'm trying to say?
So can you repeat?
Okay, look at this. This phosphorus has the fifth electron, the free electron, right?
Yes, sir.
Okay, now you think and tell me, does it have same energy level as the free electron from germanium, or it has different energy level or different energy value? Different.
Different.
It is found that this phosphorus, right, the fifth electron from phosphorus is found to have energy little bit less than what?
Energy level of germanium.
Conduction band of germanium. Energy value of
Germanium.
conduction band of germanium. Are you clear?
Yes, sir.
Okay, so this is a totally new level, right? And this new level has been formed because of what? Phosphorus. Are you clear? All of you, are you guys clear with this one?
Yes, sir.
All of you?
Yes, sir.
Yes, sir.
All of you, waiting.
Yes, sir.
Okay, so now check. Okay, if I add another 5 phosphorus, what will happen? I'll get electrons or another 5 free electrons. Another 5. Okay, let's add another one. I get another free electron. So all this phosphorus, look here, I add many phosphorus atoms, right? All the fifth electron which are not forming the bond automatically will have the energy values in this level. Can you understand? And can you see already what is the advantage, guys? What is the advantage?
We get more free electrons.
Okay, we get more free electrons. Yes, correct. But do you agree that these electrons are in the conduction band or they're below the conduction band?
Below.
So they are not in the conduction band till now, right? All of you agree, no? They are not in the conduction band. But look at the idea. Look at the advantage here. See, okay, the gap. This gap between what and what? The conduction band and what, guys? This level here, right? Do you think it is 0.7 or very less than 0.7?
Very less.
Very less.
10.
It's not 0.7. This is 0.7. Look here, the gap between from here to here is how much? 0.7. That means you can shift the electrons from here to here. That means you have to break the bonds, right? Because valence band in germanium means you have to break the bonds, right? Okay, and you need 0.7 electron volts. But look at this, you can shift these electrons very easily, and you know how much is the gap? Only 0.1 electron volts. The gap between, or the energy required for these electrons to go to which band? Conduction band is very less. They can easily go. Look at this. I'm just going to draw them easily here because the 0.1, right? The difference is very, very little. So I'm going to drop all of them from here. Okay. By the way, I did not tell you what is this name of the level called. I'm going to tell you the name of the level right now. Okay. This level, right, which I told you, it is the energy level belonging to the fifth free electron from phosphorus. We call it donor energy level. Are you clear with the name? Donor energy level. Because why? Because phosphorus, can you imagine phosphorus as if it is donating an extra electron to the germanium crystal or not?
Yes, sir.
Look at phosphorus. What is he doing? He's coming in place of germanium. Yes. He's coming in place of what? Germanium, forming 4 bonds like germanium, but also donating 1 extra free electron for the current to conduct or not?
Yes, sir.
Yes, that's why we have a name for this energy level. What is this energy level called, guys?
Donor energy.
Energy levels. But now you check. Do you realize, did we form any extra holes or no extra holes?
No extra holes.
No extra holes, because did we break any bonds or we did not break any bonds? we did not break any bonds. Check, these are free electrons, directly free, without breaking any bonds we got it. Okay, that's why we don't have any holes, because holes are produced only when you break the covalent bond and the electrons comes out of it, right? Okay, now you look at the diagram and tell me, okay, whose number is very large right now in this case? Number of
Free electrons.
free electrons is large or very, very large
Very, very large.
compared to number of what?
Holes.
Holes. Okay, so now this is how you make it, right? So now you tell me, okay, is it a conductor or better conductor now?
Better conductor.
Better conductor. The germanium, whole germanium has become better conductor. Okay, I'm going to ask you a question now. Okay, think and tell me, huh? Whose number is more, the number of negative charges or the number of positive charges?
Number of negative charge.
Negative charges. This kind of semiconductor that we got, right, we call it n-type. Can you understand? N-type semiconductor. Are you clear with what is n-type semiconductor, guys? Yes, yes. Guys, are you clear with what is n-type semiconductor? N-type means negative type. Negative type. And how did I get negative type? Let me tell you very quickly. Say, because we took what? What kind of impurity did I take, guys? A pentavalent or trivalent?
Pentavalent.
Pentavalent. So look at this. So we have done doping, yes. It's a process of adding impurity, yes. Who's the impurity atom here? Our phosphorus was the impurity atom. It is pentavalent. Because of this phosphorus, right, the population of free electrons in the conduction band of germanium has rise so much. The free electrons, their population has rise, and that's why I'm saying that, yeah, it must be called an extrinsic. First of all, it is called extrinsic because it is impure. Okay, but there are two types of extrinsic. One of it is called which one, guys? N-type or negative type semiconductor. Is it clear what is N-type, guys?
Yes, sir.
Okay, I'm going to ask you
Yes,
some
sir.
questions and some answers you have to give me right now. Okay, think and tell me. Okay, very fast, let's do it. Okay, so tell me, what is doping, guys? What is doping? Quickly answer, all of you answer.
Impurity.
Process of
Impurities.
adding impurities to whom?
Semiconductor.
Pure
Yeah.
germanium or silicon crystal, right? Okay, why do we do it? To increase?
Conductivity.
Very good.
Of free elec-
To increase conductivity, very good. Or let's say to increase the number of free charges or charge carriers. Okay, charge carriers. Okay, we do that. Okay, tell me, what are the options? We can add impurity atoms, right? Who can we add? What do you think? We can add any of them, or we have to add trivalent and pentavalent only?
Trivalent and tetravalent.
Trivalent, or we have to add
Pentavalent.
pentavalent. Okay, just in this example we have added which kind of impurity, guys?
Pentavalent.
Pentavalent. Very good. If I add pentavalent, right, like phosphorus, what happens in the energy band diagram, guys? You get an extra energy level or not?
Yes, sir.
This extra energy level has a name. What is this energy level called?
Donor energy level.
Very
level.
good. Where it is present, this donor energy level?
Below the conduction
Ah,
band.
just below. It is not below. We call it below or just below?
Just
Just below.
Just below what?
Conduction band.
band.
Very good. Conduction. Don't say conduction band. You have to say conduction band of.
Germanium.
It is just below the conduction band of germanium. And what can happen for these electrons? Tell me. These electrons can easily go to which band?
Conduction band.
Because the gap between these two
Conduction
energy,
band,
because the
actually.
energy gap between these two is very, very little. And how much is the energy gap? I told you also, right? How much is that?
0.1.
0.1. Are you getting my point? So this is how you create a lot of electrons in the conduction band of germanium compared to few holes in the
Sir.
valence band of germanium. Yes.
Sir, I have one doubt.
Yes, ask me.
Sir, why there is energy gap in this donor
Because
energy level?
because germanium, right? Germanium, what is the atomic number? Do you know? I think 32, no? Right.
Sir,
32, no? Configuration will be at 2, 8, 18, 4, I think, no? Something
Yes,
like
sir.
this. Okay. And what about phosphorus? 15, na? 2, 8, 5. Agreed, no, with this one?
Yes, sir.
Okay. So, do you agree that they have same number of protons? No. They have same number of electrons? No. So, these 4 electrons, right? These 4
Yes, sir.
electrons are valence electrons of what? Germanium. These 5 electrons are what? Valence electrons of
Phosphorus.
phosphorus. Okay, they are in same orbits or different orbits or different shells?
Differentials.
Okay, so do you know that this is the lowest energy or not?
Yes, sir.
Okay, they have high energy. Yes. Okay, so do you realize that all of them will not have what? Same energy or not?
Yes, sir.
So conduction band in germanium will have more energy, right? Conduction band in germanium will have
More
more
energy.
energy compared to what? Valence
Phos-
band of phosphorus. Yes or no?
Yes, sir.
That's why this energy level is below that. Can you understand?
Oh, yes, sir.
Now you understand, no?
Yes, sir.
Okay. So very good question he has asked. Okay, so I think you also got the idea why it is happening like that. Okay, so now you tell me. Okay, I think you're clear with this much, right, guys? All of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, okay. Then let's proceed nicely. Okay, so now see. Now let's look at the next idea here. Okay, I'll do the same thing, but this time I'm going to add what, guys? Pentavalent or trivalent now?
Trivalent.
Trivalent impurity. Okay, and example is which one? Not arsenic,
Aluminum.
gallium. Okay, aluminum or let's say gallium. Okay, so let's do that. Let's take germanium again, no problem. Germanium, I'll draw slowly, but let's talk properly. Okay, we have 4 electrons. Again, same idea. I think we'll become expert in semiconductors. Okay, if we are looking properly. Okay, now see. Again, same idea, right? I'm going to have these bonds like that. We have all these bonds, but you know the temperature may be above absolute zero, so some of the bonds may be incomplete. So we will get holes and free electrons without doing anything. Also, we will get it, right, guys? Without adding anything. Also, some of the bonds will be broken already, you know, because of high temperature or let's say thermal energy. So this electron may be out here, this electron may be out here. Already we are going to get holes and free electrons, already there. Okay, without doing anything. Okay, and you know the picture already. We have, yeah, this is the valence band. Temperature is greater than 0 Kelvin. We have conduction band. Okay, this energy gap also we have very known to us. Okay, this is a 0.7 electron volts. Everybody's happy. We have holes. Okay, if I draw 1 2 3 4 holes, we get 4 holes in the electrons in the conduction band. Okay, and this is what we know as what, guys? This is called intrinsic or extrinsic, guys, where Ne is equal to Nh. Intrinsic. Okay, this much we know. But now what we are going to do, we are going to come and add this one, gallium, which is a trivalent. That means 3 is the valency. Okay, let's do that. See, I'm going to come here and replace this gallium. Okay, gone. I'm going to bring here what, guys? Germanium gone. I'm going to bring gallium. So gallium will come with 1 electron, another electron, another electron. But do you think there's an electron or there's no electron here?
No electron.
No electron. So what is this, guys? Do you think this is a complete bond or incomplete bond?
Incomplete.
Incomplete covalent bond, because it has 3 electrons. How can it form 4 bonds, right? But this location, right, is empty, right? So yes or no? So this is like what? It is like an incomplete covalent bond, and whenever we have an incomplete covalent bond, right, that means this is going to behave like a what, guys? Hole. And the electron, right? And the electron, look at this. Who is this?
Free. Or
Free or just an electron?
electron.
Electron from where?
Germanium.
From anywhere or valence band of germanium?
Valence band of germanium.
If it is free, no, it will be in the conduction band. It is not free, it is present in valence band, yes or no? So electron from valence band of germanium, right? Okay, you know what it can do? Let me just show you. It can go and easily sit here. So what is that? What will happen now? Tell me. Electron from where can go to where? Just think and tell me. Electron from bond in what? Germanium, this one. Okay, can go and easily sit where?
Hole.
In the hole brought by whom?
Gallium.
By gallium, okay, but energy is required, so I really have to show you, okay. This hole also has energy, just like these holes, right? Let's be clear. This holes belongs to what, guys? This holes belongs to
Germanium.
this holes belongs to germanium. This free electron belongs to whom?
Germanium.
Germanium, yes. This free electrons, they belong to germanium. This holes also belongs to germanium. But look at gallium now. Look at gallium. Do you agree that this hole also will have some energy level or not? Just like the previous holes, like just like these holes, right? Let me show you where it is now. Okay, check. This is important part. Look at this. I'm drawing a new energy level, right, in between the valence band and conduction band of germanium. Okay, where it is? What do you think, guys? This new energy level that I'm drawing.
Just
It is
above the
very good. This is just above the
valence
valence band of germanium. Okay, and this has a name. Earlier we call it what, guys? This level, donor energy level, right? Now we call it acceptor energy level. Okay, we call it acceptor energy level. And this acceptor energy level contains what, guys? Or who belongs to this energy level? Holes from where?
from gallium.
From gallium. Very good. Did you understand this concept, guys? Who has this much energy? Just above the valence band of germanium. It is the holes which are coming from where? Gallium, yes. And this gap is again is about 0.1 electron volt. Very small gap. So I'm going to draw holes here, okay. Let me draw using red. Look at this. This is a hole. This is a hole here. All these holes are coming from, if I add 10 gallium, how many holes will I get, guys? How many incomplete bonds will I get? 10. Okay, so I'm going to get how many holes, guys, in this level? I'm going to get 10 holes in this level. Are you clear? And now you tell me, look at this. Look at this electron. What do you think about this electron, guys? Do you think it is free or not free? It is in the valence band of germanium, right?
Not free.
Not free. Do you agree it can easily go and sit in the hole of germanium or not? Sorry, gallium or not?
Yes, sir.
Yes. So electron can easily go from here to here. All these electrons can easily go from there to there, okay? They don't have to reach here, see, no need, because that's a very high energy requirement. But now we have only requirement of how much energy, guys?
0.1.
0.1. So all these holes, what do you think, will be free or they'll be occupied now?
Occupied.
Okay, so how many electrons have left the valence band of germanium, guys? How many electrons? 10. Very good. So look at this. So if 10 electrons, they have gone from germanium and they're going to go and sit in the hole of gallium, you get 10 new electrons, right? 10 new holes, sorry. 10 new holes in which band? Valence band of germanium. Can you understand? Now we have very large number of holes in the germanium crystal or not?
Yes, sir.
Okay. Did you understand, all of you? This one. See, this is the most important part I told you. Now I'm going to ask you. Is it okay what we did, guys? Now you tell me, number of electrons is very large or number of holes is very large now?
Number of
Holes
Holes.
is very large compared to number of electrons. Number of positive charges is very large compared to number of negative charges. So what will I call it, guys? We'll call it N-type or P-type?
P-type.
type.
P-type. P-type semiconductor. It is called P-type semiconductor. What do you think? It is intrinsic or extrinsic?
Extrinsic.
Extrinsic. Okay. How did we form this P-type semiconductor, guys? Tell me. How did we form that? By
Adding
adding, very good, by adding
trivalent.
trivalent impurity atoms, like whom? Examples are important, huh?
Gallium.
Gallium,
Aluminium.
aluminum. There should be more examples, okay? So I will talk about that, or you can check the notes, okay? So guys, can I say you all are fine with this till now?
Yes, sir.
Yes,
All
sir.
of you, okay? We'll take only one hour, okay, whenever we meet, and we will finish this chapter nicely, okay? So what is the time right now? Let me check. You guys also should not be bored, okay? Today only 15 attended. Why? Last time there were many. Eva also attended. Good. Who did not attend? Donna attended. Very good. Cordom, I cannot see Cordom. Cordom is celebrating Bihu. Roshni, I cannot see. Roshni is celebrating Bihu, maybe. Many of you are not attending. Very bad, very bad. Okay. Yes, after doing so much, okay, I think what else to tell you? I think we are done for today or what? Okay.
So,
Let me yeah, yeah.
so in that notes you have provided like negative temperature of coefficient of
Oh,
resistance.
very good question. Yes, I will talk about that. Yes. In the notes. Okay. In the notes, okay, yes. Good point, okay. What about metals? Metals, right? If we increase the temperature, huh? If we increase the temperature, what happens to resistance?
Increases.
Increases. Agree or not, guys?
Yes, sir.
Resistance increases,
Yes, sir.
or in other words, resistivity also
Increases.
increases, okay. But for semiconductors, okay, that's why you know what, check this, okay. If I calculate d r by dt, that means change of resistance with change of temperature, no? If the change of temperature is positive, then resistance also is change is positive, means both increases. If this increases, increase means positive, no? So this also increases. This ratio is called temperature coefficient, okay. This ratio is called what? Temperature coefficient of resistance or resistivity, okay. Resistivity or resistance, almost same thing right now. Basically what is meant, it means the change of resistance per unit change of temperature. In the notes, you know what, it's written like this. For a metal it is going to be positive, you can see, if the temperature increases, even resistance increases. But look at semiconductors, okay. Semiconductors, when temperature increases, look at the picture and tell me what will you get in a semiconductor if temperature increases. Will these bonds be still intact or some more bonds will be broken?
More bonds will be
More
broken.
bonds will be broken, right? Because electrons are gaining what, guys?
Thermal
Thermal
energy.
Thermal energy, and they will be lots and lots of them. So now you think and tell me, is this semiconductor becoming bad conductor or it is become much better conductor when temperature increases?
Better conductor.
Better conductor, that means resistance increases or decreases?
Decreases.
Decreases.
Do you understand? When something becomes a better conductor, no, that means its resistance is decreasing. So for semiconductor, what did you learn just now? Look at this. For a semiconductor, when temperature increases, right, the resistance, or let's say resistivity, decreases. So the change of resistance per unit change of temperature, right? Tell me, what is this? If temperature is positive, increases, right? What about resistance?
Decreases.
So it is positive or negative?
Negative.
So whole thing becomes negative. That's why I wrote temperature coefficient, right? Temperature coefficient of what? Resistivity
Resistance.
or resistivity or resistance is what, guys?
Negative.
Negative for whom?
Semiconductors.
For semiconductors. And for metals it is positive. Can you understand, Rishikesh? Rishikesh, basically it means what? If temperature increases, resistance decreases. That is the meaning of negative temperature coefficient of resistivity. Okay, now it's clear, I think, no?
Yes, sir.
Okay, good. Okay, Rishikesh used to study the notes also, very nice. So I'll send you notes today also. Okay, then yeah, I think I'm almost done with today, but let me tell you what are the points you are going to study. Okay, I'll send you some of these differences you have to study. Okay, listen, you have to study what are pure semiconductors, what are intrinsic and what are extrinsic semiconductors. You have to know the difference. You have to know the difference between what and what, guys? N-type semiconductor and P-type.
P-type.
P-type, okay. Now you also have to understand N-type and P-type. One more thing I forgot to tell you, N-type and P-type. You tell me, in N-type do you get holes or not? In N-type we get holes or not? Yes. In N-type we get electrons or not? Yes.
Yes.
But the number of electrons is
Yes.
very, very large compared to what?
Number of holes.
Number of holes, okay. So you know what? Electrons are called majority. What are electrons called?
Majority.
Majority charge carriers. Charge carriers. In what? In N-type. And holes are called, what do you think? Majority or minority?
Minority.
Minority charge carriers. Charge carriers. Okay. Okay. In P-type, do we get holes or not? Yes. Do we get electrons or not in P-type? Yes.
Yes.
Okay. But holes are very large or very large in number.
Very large
Very
number.
large in numbers. Okay. As a result, now you tell me. Okay. Holes are majority or minority in P-type?
Majority.
Majority. Yes. Okay. Holes are majority and electrons are Minority. Okay, I think you are clear with this too. Is it okay, guys? Oops. Is it okay?
Yes,
Yes,
sir.
sir.
All of you?
Yes.
Okay, then you are going to
Yes,
study
sir.
yes. Okay, then you are going to study what, guys, today? Differences between intrinsic, extrinsic, differences between n type and p type. I'll send you the screenshot right now only. Then you also have to study what are holes. Okay, these are the things you study for today. Then other things we can do next time. Okay, next time let's set up some timings again. No, can we set up some proper timings so that we are not confused?
Sir, 3 days a week.
Okay, no problem. Monday. Is it fine for all of you?
Wednesday.
Monday, Wednesday, Friday, let's make it like that. What do you say?
Sir, 7 p.m.
7.
Yes, sir.
Okay, no, everyone is fine, no? 7, or you want to change?
Sir. Fine, sir. Fine.
All of you fine, no?
Sir.
Okay, good.
Yes, sir.
So you guys are free, no? So see. Okay, so let's do this. Monday, Wednesday, Friday, 7 p.m. Okay, and what we are going to do in very soon, okay, we will start solving your question paper and everything. So just attend the classes, and please, okay, when I take that question paper, no, be there so that you understand what to study from this chapter, semiconductors. Okay, so it should not be difficult. I think you're doing fine. Okay, next time I'll tell you what we are going to do. We are going to do something called p-n junction diode. I'll tell you very quickly. Okay, then we'll stop. You know what we'll do? We'll take a p-type semiconductor. You already know what is that. And we'll take what? N-type semiconductor. We'll join them together like this. Then we'll get a device. We call it what? Diode. Okay, and that is going to have a lot of utilities. This is the most important invention, okay, of the century. Okay, you can say the century. Okay, 19th or 20th century. Okay, this is a very important invention. Okay, so this is left out. Okay, after this there are only 4 topics left. After this, applications of this diode. That's it. Finish. There's nothing else in this chapter. That's it. Okay, can you understand, guys, what we are going to do next? You
Yes,
have to
sir.
understand
Yes, sir.
p-type. You have to understand p-type and what, guys? N-type.
And type.
And
When we join them, what do we get, guys?
PN
Diode.
Diode. And how many applications of diode we are going to study?
4.
4 diodes, and this chapter is going to be over. Okay, so just be with me, and yeah. Okay, so bye bye. We'll see you next time. So bye bye, guys.
Thank you, sir.
Thank you.
Bye, sir.